What to do, everybody? Welcome back to another Spidey Physics video. In the last video, I went over this formula sheet for a standard university electromagnetism course. This is the first semester or first half of the semester where you cover the electric field, electric potential, some Ohm's law, capacitors, and some circuit stuff. This video, we're going to look at this formula sheet here, which is the second half of a typical university electromagnetism course, the magnetism and AC circuit section. Okay, so I'm going to try to do a thick video on all of these sections because this typically is the thing that's given to you in a exam. So you walk in, you have all of the questions on the test, and on the back side you have this formula sheet. So it's very good to base your knowledge off of this. If you walk into the exam and you know what each of these equations on this paper is doing and it means, and you can think of maybe one or two different problems that each of these equations relates to, then you're at a really good stage. And if you don't know how to solve one of the problems in the exam, you could just look at the equation sheet, pick an equation that you think is related to that problem, and then start expanding it. And most of the time, you'll get to some correct situation. So welcome. It's going to be a very long video. I'm going to put all of this together, and then maybe I'll do some extra videos that are specialized for other problems. But let's take a look at a global view of the equation sheet, and we'll do quick 60 seconds covering everything. Okay, so we have a couple blocks here. You could see it's broken down into maybe like 6 different blocks, maybe this one here, 7, and they're all titled. So the first one here is the magnetic force. You could see a bunch of things with the letter B in here. B, you could see B pretty much everywhere. B is the magnetic field. This is the first part of the semester. You have this equation here, which relates to this one. So you can combine these two blocks together. Force of a due to a magnetic field on a wire. Right here we have Faraday's law, inductance, and LC circuits. So we have one equation here, another one here, another one here, and another one here. 4 equations, 5, 6, 7, 8, 9, 10, 11, 12 equations. These guys have epsilon in it. Epsilon means voltage or electromotive force. You have some L's over here, which is inductance. You have this law over here, pretty interesting, and some equations for current. And then you have U over here is potential energy, and here they break down potential energy due to a capacitor C and an inductor L. And you have this equation here, and then you have omega equals 1 over square root LC. Omega is angular frequency. Cool. Then we go down into AC circuits, the last of these 3 big blocks here. The next one over here is physical constants, and these ones are boxed equations here. So these 3 chunks over here are pretty much the content of the whole semester. So yeah, AC circuits, we have phi. Z, we have some R's over here, X's, R over here, I, delta V equations, a bunch of weird stuff, I max. So AC circuits, there's current and voltage and resistance. And now we introduce capacitors and inductors, so a bunch of different stuff there. Physical constants, pretty self-explanatory. You have a bunch of letters here and what they equal, and also the units. So you can see here we got electron, 1.6 times 10 to the negative 19 coulombs. We have Avogadro's number, speed of light, Coulomb's constant again in a fancier looking way with no units. Epsilon naught, I believe this is permittivity of free space. So how easily the electric field passes through the vacuum. This is mu naught, I believe it's called, mu naught over here. I believe this is called the permeability of free space, how easily the magnetic field passes through the vacuum. I actually don't know what this is. 1T, I think Tesla, T is Tesla, and G over here, I actually don't know what it is, so take a look at that one. A couple of masses and electron volts to joules conversion. So that's the first top 4 boxes. And here we have a couple of box stuff. Kinetic energy and centripetal acceleration. Kinetic energy, K is 1/2 mv squared. Kinetic energy with a little r here, so I'm assuming that means rotational. You have I, which is moment of inertia, and omega, which is the angular velocity, which is different from the linear velocity here. Cool, maybe not too useful, but good to make sure they're there. Here we have centripetal acceleration. So an object going in a circle like this feels an acceleration, and that acceleration is inversely proportional to the radius of that circular motion, this guy, and proportional to v squared. Also pretty cool. We're going to use this guy. Arc length is s. It equals r, the radius. So if you have a circle like this and you want to find this arc length distance here, you take the radius and you multiply by the angle that that arc length produces. Boom. And then we end off with some kinematics equations from classical mechanics course: final velocity, initial velocity, acceleration, time, final position, final velocity again, final position. Angular kinematics. So omega is angular velocity instead of linear velocity. Theta here is like angular distance. And yeah, cool equations here. So a big overview. What I'm going to start with is this block here. And I guess we can get right into it. But again, a little bit of motivation. If you could look at this stuff, which is the main equations that we've learned in this course, also including this little thing here, all of this stuff here, it's pretty much a big summary of the semester. So if you can explain each of these equations, you are good to go. I would say it's very good for a final exam to study this and do some practice problems that include these equations. Cool. So in the spirit of lo-fi, I got a black background here, and we're going to start off with this equation, block of equations here, okay? We got this first equation, which is FB equals QV cross B. So you may see it written like this, F subscript B. The F is bold and it has a vector on top of it because it is a force, and forces are vectors. We have Q, which is the electric charge, or the charge of the particle, Q. Then we have another bold letter V, which is a vector. This means velocity. Cross product B. B is the magnetic field. This is analogous to the first part of the semester where you learned the electric force. This is QE. You see how they're similar? The main difference is that the magnetic field one has a cross product and a velocity here. It doesn't have just the magnetic field. So this here is electric field. This B is magnetic field. Cool. These two are charges. Charge. And this is velocity of charge. Cool. So there's magnetic fields. Let's say we have a magnetic field pointing up like this, and we have a little charged particle Q which enters the magnetic field, and it has a velocity going this way. Cool. So what you see here is actually that there is a cross product, and when you learn about vectors, there's two different types of vector multiplication. We will talk about this in another video at length, but I'll just introduce this here. The dot product and the cross product. Okay, this one you can calculate it using AB sine theta. This one is AB cosine theta. Okay, but this guy gives you a scalar, and this guy gives you a vector. So you could see over here that we have V cross B. These two are vectors and they're being cross multiplied together. And that whole thing you multiply by Q, which is just a charge. If you look back in the equation sheet, if your charge is an electron, you can plug this thing in here, which is just a scalar. This has no direction. It's just a magnitude. It's like the mass. The mass doesn't have a direction. Cool. So we do this cross product between these two vectors, and we multiply the result of that, and we get a vector on this side, okay? In this case, we just have the electric field and a vector on the other side. So when you had problems with the electric field, let's say this was the electric field, and we had a charge inside the electric field. It was just chilling there. There's no velocity. This particle will feel a force which is in the same direction as the electric field. If this charge if this charge over here is positive. Okay, if the charge is negative, you then have to multiply this vector here by a negative sign, right? You have q minus q times E flips this into the opposite direction, 180 degrees. So a positive charge would feel a force going upwards, but if I put a negative charge, let's do it in red over here, this would feel a force going downwards. Cool, and that's just a little summary of the first class. In this scenario with the magnetic field, it's a little more complicated. We have to do the cross product. How the cross product works is you use your right hand. So you have your right hand like this, right? That's your right hand if you're looking down at it and your palm is facing you. Let me actually draw this over here. Right hand, palm. Cool. So if you have over here A cross B equals another vector, right? This another vector here. Let me actually just write it over here. A cross B equals C. Okay, the cross product spits out another vector. A, let's draw it in blue, will be in the direction of your thumb, right? B, you can point in the direction of your pointer finger. And then C, you actually have to bend your middle finger so that it's coming out of the page like this. It's coming vertically up. So if you actually do this, you can point your thumb in that direction, this in this direction, and then your thumb or your middle finger will be pointing like that, and then your other fingers end over here. Check the cross product right hand rule on YouTube and you will see what I'm talking about here. Sorry, I don't have a video of this. But yeah, you can find the direction of this. So let's say we put a positive charge, right? This is a positive charge particle into a magnetic field which is going vertically upwards on my paper. This guy is going horizontally to the right on my paper. So we do the cross product, and we get that the force that this positive charge feels, positive charge. So I made a small mistake before, which is why we're back. When you see a cross product like this, always the first vector is denoted by the direction of your thumb. The second vector is denoted by the direction of your pointer finger. And the result of that cross product is the direction of your middle finger. So when these two things are multiplied together, thumb in the direction of V, pointer finger in the direction of B, and your middle finger, when it's jutting out like this, notice it's perpendicular to both of these vectors. So the cross product gives you a vector perpendicular to both of these. So if this is A and this is B, maybe these are perpendicular, then C would be coming out perpendicular to both of these guys in the third dimension. Cool. If you have a negative Q over here, then this entire vector, if it's pointing this way and you multiply by negative Q, then you would get a vector completely 180 degrees. So the mistake I made before was, well, we have an example here with a positive charge with a velocity going this way into the magnetic field. I'm going to use the right-hand rule, which means my thumb will point in the direction of V, the first vector, and this will create my hand like this. My palm will face the ceiling, pointer finger will face the direction of B, and then the direction of the vector will be this way, completely out of the page. And how we denote out of the page is by using this dot with a circle. So this is the direction of FB for a positive charge. If it's a negative charge going this direction, then you do the right-hand rule the same way because V and B are pointing in the same directions. But now we multiply this direction, which remember is out of the page. We multiply that by -1 because remember the charge over here is being multiplied by this entire thing. So first we do V cross B. We get the direction. In this case, it is out of the page. We multiply that by a positive Q. In this case, the charge is positive. So the direction of the force that that particle feels is upwards. So it enters the magnetic field and it feels a force upwards. So it's going to start traveling kind of like that. A negative charge will feel a force going into the page like that. So this charge will enter here and be pulled downwards kind of into the page. Very cool. So now that we've determined that, I guess let's go through some other cases where you have a positive charge, a negative charge, and the velocity is going this way. Right? So in this case, V is going that way. So I use my right hand. My thumb is pointing this direction. Pointer finger in the direction of B. And now my palm is facing the ground. So my middle finger will face downwards. And these are my knuckles. So in this case, the force felt by this particle, this positive one, will be into the page. Cool. And for the negative charge over here, it would multiply the vector above by -1, which flips it exactly 180 degrees. So as you can see, if you change the direction of the velocity, then the force changes. If you change the charge, so this is a negative charge, this is a positive charge, the force also changes. And then same thing here. So a positive charge entering the magnetic field is going up in the entire location over here. It enters the magnetic field and it starts getting pushed into the page because of this force. Wait a second. My bad. It gets pushed out of the page. This direction, because this is the symbol for out of the page. This negative charge will be pushed into the page. And if you flip it here, this negative charge going this way will be pushed also out of the page. V cross B, yeah, it'll be pushed out of the page like this because it's negative. And if you do V cross B with your right hand rule for this one, this will be pushed into the page this way. Cool. So now that we have that, let's take a look at this secondary equation. Remember that what we went through was this equation over here. And now let's take a look at this second equation over here. So if you remember the Fe, force due to a electric field, we have Q times E. And now we've learned this one for the magnetic field, which is a little more complicated. You have the cross product, but still you have the charge and you have the field in question. And you have the force on this side, force, and subscript E, subscript B for which force it is. Since these two are forces, you can actually add them together to find the total force, Fe plus Fb. And since you have the same charge, this is the force felt by a charge Q inside a location with both electric and magnetic fields. And the charge has a velocity V. So you can pull this Q out, keep it on the front, and then inside the brackets, you can have the first field, the electric field, and then the second thing, V cross B. So remember, V cross B gives you another vector, let's say C, and then you add that with this E. So inside the brackets here, you get a vector. Then you multiply that vector by the charge Q, and you get the total force, the Lorentz force. So that is this second equation here. And this last one, FB, you can see it is not bold anymore, and it doesn't have the vector superscript, because this is just the magnitude of the force due to the magnetic field. And you can see what it equals is magnitude Q, so the magnitude of the charge, V, which is the velocity here, again not bolded, no vector thing because it's just a magnitude, B, the magnetic field, again not a vector, just a magnitude, and sine theta, the angle between V and B. So if you remember, I showed you guys how to expand this thing over here. This gives you the magnitude of this vector here, right? Because this is just a magnitude. If you have vector A and vector B, like this is the angle theta. You take the length of A, that is this number here. You take the length of B, that is this vector here. You use sine of the angle between them, and then you get this thing over here, which is just the length of the vector over here. If you want to find the direction, you have to do the right-hand rule. Sounds good? Cool, guys. So that is the very first section, all of the equations here. Now, a couple of questions that you might see with this is, Well, remember that vectors like this can be added together if you break them apart into the components. So in the first chapter, we saw a particle that felt a force like this due to many different bodies. You have to be able to set up a coordinate system. So in this case, let's do this one. This is y and x, and you have to be able to break apart these vectors into components. So this component, this component, this component here. So this one is for this, and this one is for this, and this component here. And you have to break apart this one too. So break apart all these vectors into the components, and then you have to be able to add all of these up together to find the total force. That's the rule of superposition, adding up forces due to the forces in terms of vectors or adding up magnetic fields. Okay, now that we know this, let's move on to the second big equation, which is labeled with a name. It is called the Biot Savard Law. So we have this equation over here. Let's take a look at that a little more deeply on this equation. So what we have is dB. So this is like a differential quantity of the magnetic field. Then we have a couple constants, mu naught over 4 pi. So these are just constants. Mu naught is the permeability of free space, and it is given to you over here. So you can actually use that if you want. 4 pi times 10 to the negative 7 Tesla meters amp. Mu naught to 4 pi. On the top we have I ds cross product r, and on the bottom we have r squared. So we see another cross product there. Interesting. So I, then we have ds, which is a vector, cross product r, and I think r is a hat in this case. R hat. Yes. You see that? We have ds with the vector here and r hat like that. And then we have another r on the r squared on the bottom. Cool. So r squared like this, and this is the Biot Savard Law. Biot Savard. What is this equation? It is very, very similar to the total electric field, which you saw as an integral dq over, maybe here there's a ke, dq r squared. So this equation can be written like this, ke dq over r squared, okay? And you can see how the total electric field equals an integral. The thing you're integrating over is the charge element, and here you have an r squared because the electric field gets weaker as a function of r squared. So if here I have r like this, here I have electric field, it gets weaker as a function of 1 over r squared. That's the same thing with the magnetic field because of this r squared here. And for the total electric field, you have an integral because this integral is saying add up all of the dq's. But if you don't have that integral, like in this scenario, you still have the dq, and what that dq creates is a little dE. So dq is a super, super, super tiny piece of charge, and that creates a super, super tiny piece of the electric field. Same thing here. Super, super tiny piece of, well, what the hell is going on here? Super tiny piece of ds, that's where the d is. ds, we don't really know what ds is. It's not the same as dq. Creates a super, super tiny piece of the magnetic field. Okay. And then this ke is kind of similar to this mu naught 4 pi. If you remember over here, ke is actually 1 over 4 pi epsilon naught, right? Epsilon naught is this one. Now we're in the magnetic field section, and we have this thing over here, which is slightly different. There's no ke for the magnetic field equation. Alrighty, now let's take a look at this thing over here. This is the current, and here we have ds cross r. So why is there the current and why is there this ds cross r? The magnetic field is created by moving electric charge, and moving electric charge is change in charge over time, the derivative of charge with respect to time. If that derivative is not zero, then it creates a current, which we label uppercase I. Let's say we had a wire that was infinitely long, for example, and we had current I going through it. Let's say this is 1 amp, right? The current is going in this direction. The magnetic field is actually created around this wire, and how it looks like is you could use the right-hand rule again, but this time it's a little different. You point your thumb in the direction of the current, and then your fingers will wrap around in the direction of the magnetic field. Oh man, that looks crazy. So, anywho, this thumb points in the direction of the current. This is your right hand. And your fingers over here are curling around in circles. They're curling around this way. So if I do this right hand rule, I will see that the magnetic field is actually curling around like this. Right? So it is curling around, going above the wire on the front side and behind it on the back side. Try using the right hand rule and seeing this. So the magnetic field is created by moving current. And the Biot Savard Law is actually the most fundamental way of calculating that. And how we could do that is, well, okay, let's take a look at the wire like this. So this is the current. It's coming out of the page, and the wire has the current going around like this. If I do the right hand rule, I'll see that the magnetic field is going around this way. Okay? And the distance from the wire to where you were measuring the magnetic field, this is the magnetic field with letter B, B, B. This distance here is R, right? And as you get further from the wire, due to this little R squared over here, the magnetic field decreases. And this little ds cross R is a way of encapsulating the information that the right-hand rule holds. So the Biot Savard law implicitly uses the right-hand rule because of the cross product between ds and r over here. So what is ds and r? ds is the direction, or it is the distance, or let me see how I can explain this. So dr is a little piece of the wire, or a little piece of the radius, which goes from the wire to the magnetic field, and it is a magnitude of 1. So whatever distance away from the wire you are, let's say this is the wire here, if I go perpendicularly upwards, let's say like 3 meters, right? And I measure the magnetic field here, what is the magnetic field? Well, I can break it apart by first labeling this distance r. So r is equal to 3 meters. And over here, I can break apart this little tiny vector, which is a direction of r, and I'll call this r hat. R hat. And ds, I'm assuming here, let me see. ds is the direction of the current in the wire. So the current is going in a wire, and you could see over here, the wire is going this way. I will call this little piece over here, this is ds, and it's going in a specific direction. Okay, it's going in the same direction as the current. So okay, now take a look at this. Remember how I told you guys to do the cross product with the right hand rule? Let's take this thing inside the Biot Savard law and do the right hand rule there. Okay, I already defined the direction of ds. ds is going this way, and I defined the direction of r hat. R hat is going this way. So remember, thumb points in the direction of the first vector, pointer finger points the direction of the second finger, and then the result of this will give you the final vector, maybe as vector c. In this case, the final vector is, it's literally on the other side of the equal sign. So here we have a constant, here we have a constant, here we have, actually these are not constants, these are constants. This can be a constant, but what I meant to say is all of these things are scalars. If all of these are scalars and this here is the only thing that includes vectors, then you have ds cross product r hat, and this whole thing, if you multiply it by these little quantities here, will give you the direction of dB. Okay, so now that we know the direction of dB around a wire, it's going around and following the right-hand rule like this. So if the current is coming out of the page like this, magnetic field is circulating counterclockwise around the wire. Now let's take a look at a side view picture of the wire. Current is going this direction, which is the ds direction, and I want to find the magnetic field a distance r away from the wire itself. So we have r hat, the direction which is perpendicular. Boom, this way. So I use my right hand rule and I do thumb in the direction of ds, pointer finger in the direction of r hat, and my middle finger is pointing directly out of the page like this, right? So what I can do over here is B is going out of the page. So this thing here told me the direction of the magnetic field, which is going out of the page. And that works with the right-hand rule, because take a look at this. If this here is going out of the page, then I can do the same thing for any R over here that is 3 meters above the wire, and each location there, the magnetic field will be coming out of the page. Makes sense? That is the same thing over here. You can see the magnetic field is coming this way, which you can write it as out of the page, like that. If you go on the bottom side over here, the magnetic field is actually going into the page. So you can write it with all these X's. Let's do that thing right over here. So again, I have the direction of ds, except now I want to find the magnetic field below the wire. Let's find the magnetic field at this point P, a distance r, and this will be a distance. This will be r hat. So I use the right-hand rule again. Remember, thumb in the direction of ds, but whoops, now I have to flip my whole palm so that my palm is like facing downwards. So basically I'm doing the right-hand rule like this. Thumb in this direction, pointer finger in this direction. Now my palm is facing downwards into the page, so my middle finger is going like that. You guys see? So at this location, this is going into the page. So this is what the Biot Savard Law does. This ds cross r tells you the direction of the magnetic field. The magnetic field depends on the current. So if the current is much greater, this number is very big, and it makes this number very big. This r squared is on the bottom, so the further you get from the wire or the source of the magnetic field, then the weaker this thing becomes, right? If I get really, really close to the magnetic field, like r is equal to 0.1 centimeters, then the magnetic field will be really big. But if I go here, r is equal to 10 kilometers, then I'm dividing here by 10 kilometers, which is a lot of centimeters, and the magnetic field here decreases. So that is what the Biot Savard Law does. It finds the direction of the magnetic field exactly like how this equation for the first part of the semester was calculating the electric field. Cool. Now that we have that down, that is the main law over here, but it's actually not going to be that useful. It's good to know how it works, but over here you can see they actually calculate the magnetic field. They give you B is equal to all of this jumble, and it tells you infinite wire. Then they tell you B is equal to all of this. It looks very similar. This jumble here looks like this jumble. You have mu naught I on the top. On the bottom you have 2 pi a, and on the bottom here you have 4 pi a. So very similar. And here you're being multiplied by these sine of the angle things. And this is telling you for an infinite wire what the magnetic field is, and for a segment of wire what the magnetic field is. Let's see if they do that anywhere else. So they actually do it over here. B is equal to mu naught n times I over L, or mu naught is lowercase n times I, and they tell you solenoid. So this is the magnetic field of a solenoid over here. Same thing over here. They give you magnetic field equals all of this stuff, mu naught n I 2 pi r, and they tell you toroid. So they actually, you can imagine that the equation sheet uses the Biot Savard Law. and it actually calculates the magnetic field for several shapes over here, 4 different shapes. This is another equation, this is another equation, but all of these here, here, and here, those are magnetic fields of specific geometries: infinite wire, segment of wire, toroid, solenoid. Cool. So that's the Biot Savard law actually used over here and over here. I'm gonna like explain to you guys kind of how you get these equations and how you get them. Of course, you can use Biot Savard law, but it's a little bit overkill. It's like opening a can with a shotgun. What you should actually use is this thing over here, which is called Ampere's law. So Ampere's law is over here. So what I'm going to do is I just spoke to you guys about this equation. Maybe take a look on YouTube, Biot Savard law, see if you kind of understand what all of the moving pieces are like in here. But I'm going to jump very quickly to introduce the Ampere's law, and I'll show you how this equation is actually much easier to use if you want to calculate this and this and this. And then we'll end off with this guy. So now that we've learned the Biot Savard law, let's go to the next equation, which, like I said, is Ampere's law. Ampere's law looks very similar to Gauss's law, except here you have a 2D Amperian loop. What you're integrating over is B dot ds. Both of these are vectors because of the dot product. And what this equals is mu naught, the constant that you have in the equation sheet, and I enclosed. So this is very, very similar to Gauss's law, which I will write over here. Ampere's law, Gauss's law, let's cut up over here. So Gauss's law, if you remember, was an equation for electric and magnetic flux. So the equation works for both of them. You'll see how similar they look here. The integral here is also a closed integral, except here it's over a Gaussian surface. Same thing for the bottom side. Let's actually write that down. Gaussian surface. For the electric one, what you're integrating over is the electric field dot product dA in this case, which is different from ds for Ampere's law. And for the magnetic field, you just have the magnetic field, the dot product dA. That is on the left side, and then we have an equality. And for the magnetic field, we actually have 0. But for the electric field, we have Q enclosed over epsilon naught. So you could see the similarities here. First of all, the form of the equations looks very similar. You have one thing on the right-hand side, one thing on the left-hand side, an equality. One thing, actually, forget about this thing over here, but you have an integral with a dot product of 2 vectors on this side. On the other side, you have just a number. In this case, it's a 0. The main differences are Ampere's law here uses the magnetic field. Gauss's law uses whichever field you want to use for the flux. So it could be the electric field, it could be the magnetic field. But the main difference is here, the second vector that is in the dot product is dA. This means an area. That's why they use the letter A. Same thing for here. And that is very, very linked to the integration over the Gaussian surface. So if you guys remember, original integrals that you first learn about, it could be some random function like that, right? And you want to find the area between this B and A. So the area in here is basically breaking apart this thing into a bunch of tiny little slivers. These slivers have a distance over here. You could call this distance dx, right? And the height of the function over here, you can say that the height is literally y of x, right? You plug in, let's say, you plug in a, this thing over here, into the function y, and whatever y of a gives you the height of the function. So the height over here. So if you multiply those two together, you multiply this dx by this ya, you actually get the area of one of these slivers. It's just a rectangle. So you can use an integral. Well, basically, you could do the height of that little sliver times the length of that little sliver. And if you integrate that, from A to B, then you get the area of the entire thing, the area of the entire bounded integral area over here. Cool. When you're using these integrals here, you have to look at what the bounds are. So for the Ampere's law, you have B dot ds. In this case, ds over here is a distance. And this 2D Amperian loop, it could be like, for example, a circle. So this thing, you could quantify each little part of this loop as having these tangent lines, which are called ds, and they are vectors because they have a direction. So in Ampere's law, you create an Amperian loop. In this case, I chose a circle. You could choose a square, right? That could be your Amperian loop. And for each of the scenarios, you can define a direction for this ds vector. Okay. So once you get to the stage where you have an integral ds like this, it's basically telling you add up all of these tiny little ds elements, add up all of these, and basically it's saying add up all of these in this integral, except instead of giving you bounds like this, a to b, the bound is over this closed, that's why you have a little circle here, 2D Amperian loop. So this integral here is telling you add up all of these little distances. How much do you add them up? You add up all of them around the shape. So this gives you, in the case of a circle, it is the circumference of the shape, or in the shape of a square, it is the perimeter. So a little bit different from the area used in a classic integral. This thing gives you the circumference or the perimeter of the shape that you've chosen. And that is also completely different from Gauss's law, which was like this, and a Gaussian surface. So a surface is actually a 3D object, and in Gauss's law, I'm not going to go over Gauss's law here. Maybe actually you should check out my Gauss law video if you have questions about that. I think I went over it pretty well. Gauss's law, you basically break up the shape into these tiny dA elements. So in Ampere's law, we broke them down into ds's. That's why Ampere's law has a ds over here. In Gauss's law, we break it down using dAs, which is little areas of the Gaussian surface. So all of these are dA. And what you're doing here, after you manipulate this integral a bit, you will have something dA like this. So what this is telling you is it's an integral followed by a little dA. It's basically telling you add up all of these dAs, all of these tiny pieces that you've broken down your Gaussian surface, add them up, and what is the bounds? The bounds are the Gaussian surface, the entire shape you chose, and there's a little closed circle here, meaning add up all of the dAs around the entire Gaussian surface. So what does that equal to? Oops, sorry about that. That literally gives you surface area, which is very different. So in Ampere's law, the integral is in terms of distance, and it gives you a circumference or a perimeter depending on the shape that you choose. Right, the shape that I could choose for Gauss's law could also be a box like this. And in this case, the surface area of a box would be different than the surface area of a sphere. Okay, that is a bit of just the background of what I'm taking a look at when I look at these equations. And also, no need to worry about Gauss's law for now. I kind of just included it here so that you guys can see the difference between Gauss's law and Ampere's law. So I'll leave those two there. How do you use Ampere's law? Well, it's very similar to how you used Gauss's law back in the day. Sorry about that. Basically, well, let's start with the wire. We'll just do a quick wire example like this. So we know that the wire creates a magnetic field, and we know that the wire has a current. So what we could do is enclose the shape symmetrically by an Amperian loop so that the Amperian loop lies at a distance r. This distance puts the Amperian loop exactly at this point P, and that is the point where we will find the magnetic field. So we want to find the magnetic field a distance r away from a current carrying wire. And what is the wire that the current is carrying? Let's call it just capital I. Maybe it's 1 amp, whatever. So you first have to create an Amperian loop. Just like how Gauss's law, you had to create a Gaussian surface. You'll get used to doing these when you do more problems. Take a look at Ampere's law for different geometries. For now, I just want to show you guys how the equation is used. So let's write down Ampere's law, which is B dot product ds. Both of these are vectors. This equals mu naught I enclosed. Now, I enclosed is the current enclosed by your Amperian loop. In this case, my Amperian loop is completely encapsulating the entire wire. So I can expand this equation and just say I enclosed is capital I or 1 amp. I'm going to leave it as I to solve the problem symbolically. The next thing I can do is this dot product. I can expand it using the dot product identity. So B ds cosine theta. I can always do this. And when I do this, it removes the vectors on B and ds. So now they just become magnitudes. Another thing I can say here is that just from like knowledge of working with these problems, I know that the magnetic field at distance r will give me a certain value. So whatever that number is, it will be the same strength all the way around the wire due to symmetry. So if I have the same radius here and the same radius here, I know that the magnetic field here will be the same strength as the magnetic field here. Obviously, the direction will be different, but the magnitude at least is the same. And if the magnitude is the same, I can pull this b out of the integral. So I have b ds. Cosine theta in this case is the angle between ds and b. I have not chosen the direction of ds, but since I've drawn the Amperian loop, I can just choose ds to go like this, counterclockwise. Let me actually use this color here. So this is just my personal choice of ds. Whatever direction you choose, just stick with it. It's kind of like choosing on a Gaussian surface. Remember when you broke down the shape and you chose that dA goes outside of the shape? This was just kind of convention. In Ampere's law, you can choose the direction of ds to be whatever you want. Then you can use the right-hand rule, which is the one with the thumb in the direction of the current. So my right hand points thumb in the direction of the current, and then my fingers here wrap around in the direction of the magnetic field. So you guys see how I'm doing that? This is my right hand. My fingers are curling around this way, and my thumb is pointing in the direction of the current. If I change the direction of the current, then my thumb will have to point this way, and my fingers will wrap around like this with my palm facing, so I will get a different direction. So the right-hand rule, check out on YouTube, right-hand rule, direction of magnetic field due to a current carrying wire. And you'll see that the direction of the magnetic field, which I will draw here in blue, is going around this way. So exactly at this point, I will have the magnetic field going down. Exactly at this point, magnetic field will go this way. Exactly at this point, magnetic field will go this way, and so on and so forth. It will create a circle counterclockwise like this, which turns out is actually the same direction as ds. So if b and ds are pointing in the same direction, then cosine of theta, the angle between them, theta will be 0 because ds and b are pointing in the same direction all the way around the circle. Does that make sense? So now I have cosine of theta, which is cosine of 0 degrees, which actually gives me 1. If I chose ds to go the opposite way, then I would have cosine of 180 over here, which just gives me -1. So depending on which direction you choose ds in Ampere's law, you would just get a -1 or a +1, which at the end of the day doesn't really matter because you want to just take the magnitude of the magnetic field most of the time. The way you determine the direction is with the right-hand rule. So cosine theta is cosine of 0, which gives me 1. Now I have Ampere's law looking like this. And remember what I said before, this integral now is telling you integrate every piece of ds around this little circle, which is around the entire Amperian loop that we've chosen. So in this case, this is literally the circumference of a circle, and the circumference of a circle with radius r is 2 pi r squared. Sounds like area to me. If you need the circumference, just use pi d. So pi d, and the diameter is 2 times the radius. So we get that. Amazing. I'm going to keep this just over here on the side, and I can manipulate this equation again. 2 pi r. I have mu naught over here, and now I could just move 2 pi r on the other side by dividing by it, and I have mu naught I over 2 pi r. And I have the equation for the magnetic field created by a current carrying wire with current coming out of the page like this, and at a distance r. So you can see as I grow the distance, the magnetic field here is divided by a big number, so the magnetic field decreases. The current here is on the numerator, so if I increase the current, I increase the magnetic field. Take a look at this. Current of a infinite wire is mu naught I over 2 pi r. This is using Ampere's law. So going back to this equation here, I used this equation, Ampere's law, which looks like this and like this. There is no I enclosed over here, but just remember, you choose the Amperian loop and this becomes I enclosed. And I literally just calculated this, mu naught I, 2 pi, and they use A instead of R for the radius. Whatever, just keep that in mind. Cool. So for this, you can use Ampere's law to calculate it, or you could just look at the equation and remember that this is the magnetic field of a wire. Now let's quickly take a look at this equation over here. Magnetic field due to a segment of wire. So for Ampere's law, what I did was I used an infinite length of wire. If I had a wire that was instead, let's say like this, and the distance here is like 2 meters, for example, and I want to find the magnetic field at this point, P, I can draw these lines going from the edge to the point here and the edge to the point here, and I can get these angles here, theta 1 and theta 2, right? If I take this point here, if I take this point and move it around like here, or move it lower or move it up, I would just change the radius. For example, here this is the radius, and I would change these angles theta 1 and theta 2. So this, they actually give you the magnetic field. It is again mu naught I on the top. You have, in this case, instead of 2, it is 4 pi A or R, whatever it is. That would just be the length of this. That's A. Right? And here they have sine of theta 1 minus sine of theta 2. Sine theta 1 minus sine theta 2. So whatever the case is, you can plug in these numbers here to wherever, like whatever angles you get here, you can plug them in. This thing, you will just get a number, multiply that number by this, and you'll get the magnetic field at this point due to a finite wire. Okay, let's actually take this equation and quickly expand it to see if it works for an infinite wire. So what I'm going to do here is just rewrite the equation. 4 pi A, and then here I have sine of theta 1 minus sine of theta 2. And let's say I have an infinitely long wire like this, and I'm looking for the magnetic field a distance here, which is A above the wire. If I extend this wire infinitely long, then these original angles that I have would be growing and growing, and eventually they would hit exactly 90 degrees. Do you see what I'm saying? So this angle here, which is theta 1, would equal 90 degrees for an infinitely long wire. And same thing for the other side. So this side we have, boom, this creates an angle of 90 degrees. So if I plug in 90 over here and 90 over here, Sine of 90 degrees is, so sine of 90 is actually equal to 1, but the way this angle is measured is actually from the normal line all the way to where the thing ends. So this you could denote as positive 90. This would actually be negative 90. And the reason that happens is because, well, sine of 90 degrees is 1. And if you have sine of 90 minus sine of 90, you get 0, which gives you magnetic field equals 0, which is not correct. So here you actually have sine of negative 90, which gives you negative 1. So in the brackets, what you get is 1 plus 1, which gives you 2, and this 2 cancels out with the 4 over here to give you mu naught I over 2 pi a. So basically, what I showed you guys here is if you take this equation that tells you the magnetic field due to a finite length of wire, due to a segment of straight wire, this guy here, and you apply these angles to be for an infinitely long wire, then this equation here reduces to this equation here. Okay, cool. Now let's quickly take a look at the toroid and the solenoid. So if you have learned about what a solenoid is, basically you take a wire like this, and if you wrap it around kind of like an old school phone cable, then you get a loop of wire like this. And because the way the current flows, like let's say the current is flowing this way, what you get is all of the magnetic field kind of collecting and getting strong inside of this solenoid. So a solenoid here has length L, it has a number of turns, which is capital N, and it has a current running through it. And inside you get a strong magnetic field, which is unidirectional. It's kind of like when you had capacitor plates for the electric field, and you saw that in here you created a strong uniform electric field. The solenoid is like the magnetic field version of that. And if you want to actually see how it works, just apply the same kind of analysis we did for a straight wire, except first imagine the wire was looped around in a loop like this. See what the magnetic field looks like inside and outside the loop. And then imagine you combine a bunch of loops like that together and see what the magnetic field looks like inside and outside the loop. Okay, so one way you can use the Ampere law to solve this equation is you can create an Amperian loop. And in this case, the Amperian loop that we will choose is a square or rectangle. Let's say it has length x and height y. And we're going to put a portion of this Amperian loop inside the solenoid, and the rest of it will be kind of jutting out like this. So you might ask yourself, like, why would you choose this Amperian loop? Let's just stick with this one. Take a look at Ampere's law in further detail if you were wondering about that. But let's rewrite Ampere's law here and take a look at how we can solve this problem and get an equation for the magnitude inside a solenoid. So this here is a solenoid. Cool. Our Amperian loop is here, and let's actually define the direction of ds. I'm going to again choose that it's going counterclockwise, ds like this, ds like that. That means here it's going this way, and here it's going this way. Cool. Now that we've chosen the direction, I will just expand this dot product in terms of this identity. Magnitude of the first vector times magnitude of the second vector times cosine of the angle between them. That is the dot product identity. And let's actually take a look at what the current enclosed is. So if I do this with my Amperian loop, I can see that over here, some parts of the wire are coming through and then they're going in like that, right? So I actually enclose certain portions of the wire. How many of these portions do I enclose? Well, I actually enclose n, the total number of actually, hold up a second. N is the total number of wounds of wire you have over the whole solenoid. And the current enclosed is only the current enclosed by my Amperian loop here. So here we have, um, okay, you know what? Let's actually say that the letter N denotes the number of times that the current or wire passes in our Amperian loop. Then we can just say the current enclosed is N times I, N being the number of times the wire loops around, and I being the current. Cool. Now that we've done that, I'm going to actually expand this integral because, as you can see, there are 4 different sections here which different behavior is happening. One section, the Amperian loop, like this part of the Amperian loop, is actually inside the solenoid. This one and this one look kind of similar. A part of this piece of the loop is inside the solenoid, but the rest of it over here is outside. And this part is actually completely outside the solenoid. So what I'm going to do is expand this integral in terms of the top, the left side, the right side, and the bottom of that square loop. And I can just add all of these integrals together. And inside these integrals, I have the same thing here, b dot ds. Okay. So what you have to know about a solenoid is that if you use your right hand rule, so you can curl your fingers in the direction of the current. In this case, the current is going like this, kind of like it's entering here and circulating around like that. So just point your right hand, the fingers, the 4 fingers of your right hand, in terms of this, and your thumb will point in the direction of the magnetic field here. So you could see the magnetic field here is going this way, but ds on top of the loop is going this way. So cosine theta for this top thing, b ds, is actually going to be -1 because we have cosine of 180 degrees. So I have a -1 there, and then I have b ds. Okay. For the left side, we can make an argument for actually all of the sides here. This side, and this side. We're going to say that the magnetic field B is so small in these areas that basically B over here equals 0 for all of these, 0, 0, 0. And if you can say that, 0, 0, 0, then all of these integrals disappear, and this entire thing over here can just be simplified as this, -1 BDS of the top side, mu naught Ni. Is that okay with y'all? Now, along the top side, the magnetic field is actually constant and uniform. That's something you learn about a solenoid. The magnetic field inside the solenoid is uniform, and it doesn't change in strength too much. That's the value of a solenoid. And because of that, you can pull this b out of this integral. So I have -b ds top equals mu naught I. Now, this thing, integral of ds on the top side, is literally saying, hey, all of these tiny ds things on the top side, just add them up all together. And when you add them up, what you get is just the length of x, which is predetermined. Like, you choose that. So basically what we have here is bx equals mu naught I, and I can do b and move the x on the other side. So I have mu naught, oh, my bad, I missed an n over here. This n follows through, right? So I have mu naught n, I'll do n over x, I, and this is actually the equation shown to you guys here. So you can see solenoid, the mu naught n and I. The only difference is they used L for the length over there. Normally this L, you could say, is the length of the solenoid. So if I want to find the magnetic field of the whole solenoid, I can just create a big Amperian loop like this, and this entire thing would be the length of the solenoid. In this case, I just chose a small one like this, so the length of this thing I called x. But you can see it's the same thing. Mu naught n over x. This n over x is n over L in the equation sheet, multiplied by I. So, oh, and also another interesting thing is They actually write this N over L as lowercase n, and you'll see it written like that in the equation sheet 2. So you have this thing right here, N over L equals lowercase n mu naught 0, N over Li, mu naught 0, lowercase n I. That is the magnetic field inside a solenoid. So what that means is you have a solenoid, and if you increase the current on the solenoid, so boom, I increase this current, the magnetic field inside the solenoid gets bigger, right? Because they are directly proportional. Equal sign B, equal sign I. If I change the current density, this is, or sorry, not the current density, the wire wraparound density. So this little n is literally number of times the solenoid has wires wrapping around it divided by the length. So you could say it's the loop around density, right? If this number increases, that means I have a really, really finely packed solenoid with a lot of wires. But if this lowercase n decreases, then I have kind of a loosely wound solenoid like that. So if I increase this, I either increase the number of turns or decrease the length of the solenoid for the same number of turns. I increase the magnetic field of the solenoid, and mu naught is just a constant. So this is a very quick way of using Ampere's law. Ampere's law I introduced over here to find the equation of a solenoid, but it's also just written for you over here. Cool. So we went over infinite wire, segment of wire, and solenoid, and we went over how we can use Ampere's law. Remember, all of this comes from the Biot Savard Law, but Ampere's law is much easier to use in a pinch. It's like using a can opener for a can instead of here using a shotgun to open a can. A toroid, I'm not going to go into it very much. Imagine you have a solenoid like this, and you just take this solenoid and wrap it around in the shape of a donut. You have the magnetic field inside the donut, and this is the strength. Radius is from the center of the donut going outwards, and N is the number of wounds the donut has. I is the current inside of the donut, and we have 2 pi r. If you want, take a look on YouTube how to find magnetic field of a toroid using Ampere's law. Cool. So now that we've looked at all of these equations, we've looked at this guy, we've looked at this guy, and we've looked at this guy. Then we took a quick look at the Biot Savard law, and then we looked at how there's 4 different geometries that create magnetic fields. Each of them has current, right? You need current to create a magnetic field. And in this case, we looked at a wire, infinite length and finite length, a solenoid and a toroid, and Ampere's law. So we're going to finalize this section with this thing over here. FB over L is equal to mu naught I. It looked kind of similar to the equation of a wire over here. And what this is well, I'll show you right over here. So remember how we learned there's wires that carry current, and due to the Biot Savard law and using the right-hand rule, you could see that they actually create a magnetic field that goes around like this. Using the right-hand rule, thumb in the direction of the current, fingers wrap around in the direction of the magnetic field. If you have another wire over here, and it also has current running through it, right? Current running through it. It will also create a similar magnetic field. Boom, 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 magnetic field. Now, if these wires are close together, right, let's say they're a distance r apart, the magnetic fields will actually interact and the wires will feel a force between them. This is very cool. If you see high current wires, well, any wire, let's say you plug your phone into charge, that wire has current running through it. It creates a magnetic field around it, circulating around the wire like this. Very interesting, right? That magnetic field, if you remember from the very first equation we learned, that magnetic field creates a force on a charge Q if the charge has velocity v and the charge is inside a magnetic field B. So, okay, take a look at this. A wire over here creates a magnetic field and it circulates around like this. As you get further from the wire, like here or here or here, the magnetic field decreases in strength because you're getting further from the wire. If you're very close to the wire, the magnetic field is very strong. And what the magnetic field of a wire actually looks like is mu naught I, 2 pi r. This is magnetic field of a wire. Cool. If you have another wire nearby, that wire, this wire here, yes, it has current and it creates its own magnetic field, but think about what current is. Current is actually a bunch of charges with a velocity. So in this case, there's a bunch of charges here inside of this wire, and they're all going this direction. Okay. Now, because of this equation, we can actually calculate the force that each one of these particles feels due to the magnetic field of the other wire. Okay, so let's point our thumb in the direction of current, and we will see the magnetic field wraps around this way. So exactly at this point, the magnetic field of the wire above will be going into the page. Is that correct? Yes, because imagine this thing, boom, it points into the page right at this stage, right? All the way above the wire over here, this wire here will be creating a magnetic field coming out of the page. Right, and then above it'll be going from up to down like this, circulating around. Cool. Okay, so because of that, we can now use the right hand rule, this one with the thumb, to point our thumb in the direction of velocity, our pointer finger in the direction of, so we have to do thumb in the direction of velocity of the charges in the second wire, pointer finger into the page, and this middle finger will be pointing downwards, and here are the rest of your knuckles. Okay, so what did I show here? This is V, the velocity of the charges in the current. This is B, the magnetic field created by this wire above here. And this is FB, the force that a positive charge feels in this wire due to the magnetic field of this wire. If the charges inside this wire were negative, then you have to multiply this vector by a negative sign, which flips it exactly 180 degrees. So, to summarize, if there's electrons in this wire, they would feel a force going this way due to the magnetic field of this adjacent wire. And similarly, if I point my thumb in the direction of this wire, the thumb in the direction of the current, and then my fingers wrap around in the direction of this magnetic field, then if I look at a distance over here, r, exactly at this wire, the magnetic field of the bottom wire will be pointing completely out, right? And over here, it would be pointing completely into the page, right? It's coming out of the page and going into the page here. Out of the page, into the page, right? The same thing I drew here, out of the page here, into the page here, okay? Now, if I use the right-hand rule for this equation onto this wire, I can point my thumb in the direction of the velocity, right? The velocity of the charges, which is the direction of the current. I can point my pointer finger, in this case, thumb here, pointer finger out of the page, and then my middle finger will be pointing exactly downwards. So this is downwards is the direction of positive charges. Okay, all of that to say that the equation that you get here, FB over L, is equal to, let's actually check what this equation looks like. So we got FB, this is the force due to the magnetic field. L is the length of wire, so if you have force per length, it's force per unit length. So how much force each little piece of the wire feels, it is straight up equal to mu naught currents of both of the wires multiplied together over 2 pi a. Perfect. Mu naught current of the first wire multiplied by current of the second wire, 2 pi a. Cool. Awesome. So I guess a problem you can think about with this is, let's say we have this wire, its length is 2 meters, and its current is current 1. We have another wire here, this current is 2. Let's say this current, it's going this direction, and is going this direction. The both currents are both going that direction. This current is 20 amps, and this current is 10 amps, right? They're going to create magnetic fields both going in the same direction. So the force hold up. V cross B, boom. V cross B, boom. Okay, so the force these wires will feel is towards each other. So these wires would actually pull each other towards themselves. If the current actually flipped for one of the wires, current is going this way and this wire, current is going this way, then these wires would actually push themselves apart a little bit. And how you can calculate this, well, the magnitude of the force, you can get the length of one wire, 2 meters. If you want, multiply that here, length. So the force that you get between these wires is straight up mu naught, current of the first wire, current of the second wire, length of the wire that you want to find the force on. And then you have 2 pi a. A is the distance between the wires here. Cool. Alrighty, so to summarize, let's go back to the original equation here, the equation sheet. We have the force due to a charged particle with velocity v in a magnetic field B. If the particle has zero charge, then 0 times whatever this cross product is gives you 0. So a particle with no electric charge will not feel the magnetic force. If B is equal to 0, V cross 0 gives you 0. 0 times Q gives you 0. So force will be 0. So if you have no magnetic force, a charged particle will not feel a magnetic force. If you have no magnetic field, the charged particle will not feel a magnetic force. If V equals 0, 0 cross B gives you 0, and 0 times Q is 0. So a particle with 0 velocity will actually not feel the magnetic force, which is different than the electric field. For the electric field, if you just put the charged particle in here, if it's positive, it would go in the direction of the field. But if the magnetic field is there and the charged particle is just resting there, V is equal to 0, then it would not feel this force. Here is the Lorentz force. It is basically the electric field and the magnetic field forces combined together into one force equation. This is what you would use if a charge is placed in a location with both electric and magnetic fields. And this is the magnitude of the magnetic field. Magnitude of Q, magnitude of velocity, magnitude of magnetic field, sine of theta, the angle between V and B. The Biot Savard Law tells you that a magnetic field is created by current. The direction of the magnetic field depends on ds. ds is the direction the current is going. So if you have a wire that is like this and the current is going this way, then you can break apart ds into all of these tiny little things, ds. And r is from ds, from the wire to the point where you want to find the magnetic field. R is this thing here, and r hat is just the unit vector pointing in the same direction from the source of the magnetic field all the way to the point. And then here you have r squared, meaning the magnetic field decays proportional to 1 over r squared. Here you have some units, mu naught over 4 pi. So this equation can be used to find magnetic field due to different geometries, wires or toroids or solenoids, but actually Ampere's law is much easier to use. Take a look at Ampere's law. I might post a video doing a bit more problems on this, but for now, just know that you can use Ampere's law to find magnetic field of an infinite wire, which is this, mu naught I, 2 pi A. I is the current in the wire, A is the distance from the wire to the point where you want to find the magnetic field. Magnetic field of a segment of wire, right? The angle's here. Remember that sometimes you measure this angle in terms of a negative angle. So that negative pops out over here and it makes this plus sine theta plus sine theta. All right. Then we have magnetic field of a toroid, which is like a solenoid wrapped around in a donut shape. That creates a strong magnetic field in the center of the toroid, the solenoid, and the force between two current carrying wires. All of that here is the first section. And I actually wanted to complete the first section by also mentioning this equation here. So as you can see, this is very similar to this first equation. FB equals, in this case, we have I, which is different from Q. I is the current, Q is the electric charge. We have L. L is a bold letter with a vector quantity. This is just the direction of the current in the current carrying conductor. So if you have a wire like this, then L would be in the direction that the current is going, bold L. Very similar to the velocity here, if you have a wire like this and all of the charge Q is going this way, then its velocity is going that way, the current is going that way, and also L, the vector describing the direction of the charge and the current, is also going that way. So very similar to this equation here, and you have the cross product. You can use this equation here to find the force on a current carrying wire, which is where you get this equation from. So you have FB is equal to I L cross B, right? If I have a length of wire and yeah, I have a length of wire, the current is going this direction and the magnetic field is up like this, then I can do thumb in the direction of I, which is the same direction as L, pointer finger in the direction of B, which is the second vector in the cross product, and F is the force that I would feel on this wire, which is coming directly out of the page like this. That is the cross product. And this thing here is literally just the non-total version of this. Remember how this equation here, if you take an integral, this integral removes this little d, and this integral removes this little d here. So this equation is the same as this equation, except you just take an integral on both sides. This integral turns this ds into an L, right? Integral ds from A to B, if this is your wire, right, and this is the little ds that you're breaking down here, ds, and this is part B and this is part A. This whole thing, this integral, is basically telling you what is the length from A to B, length. So this little ds, when you take an integral, it turns into the L. So this equation here, not too important, mainly focus on this one. But again, this one not too important because it mimics the same behavior as this one, except this one is talking about a charge Q with singular velocity V. This one is talking about a collection of charge I with the collective direction L. Okay, now that we've covered this is the whole first part of the semester. We're going to take a small break before we get into these heavy hitters because that's pretty much 1/3 of the course. So we have this, that's 1/3 of the course. Try some problems with that. One big problem that I actually have seen quite a lot is this problem here. So let's say you have 4 wires that are set up like this, right? If I look at them over here, if I look at them like that, the wires look like this, right? So you can imagine they're going in this direction. And they're all a specific distance from each other. So this distance here is, let's say A, and let's say they're set up like a square, A. We want to find the magnetic field at this point, P here, right? And the current in all of these guys is going in different directions. So let's say here the current is coming out of the page, Here it's going into the page, And they all have a current of 1 amp. So how you can solve this problem is, well, you want to find the magnetic field at this point. You can use your right hand rule to point your thumb in the direction of the current. So in this case, my thumb in the direction of the current, and my fingers wrap around this way. So my fingers wrap around this way, telling me that the magnetic field due to this wire, since the current is going this way, wraps around in a circle like this. That means if I go to this point P here, the magnetic field will be in a tangent pointing exactly upward like this. Okay, so I'm going to just draw an arrow, magnetic field upward like this, B. I can do the same thing with this guy. So thumb in the direction here, and my fingers are all wrapping around this way. This is the right hand rule. So magnetic field is again going this way. And if I look at exactly point P, tangent to that point, the magnetic field is going exactly this direction. Okay, this is again B. Now let's take a look at the other wires. In this case, my thumb is pointing into the page, and my fingers are wrapping around this way, right? So magnetic field is going around this direction. So since it's going around like this, then exactly at the point P over here, magnetic field is going this way. It actually is going the same direction as this B. And if the wire carries the same current, this wire, this wire, this wire, and this wire carry the same current, then these vectors here, since they are the same distance away, right? The distance from here to here, let's say, is distance r. Distance from here to here is distance r. Distance from here to here is r, and distance from here to here is r. Then the magnetic field here will actually be the same length. Cool. Now let's do the last wire here. Point my thumb in the direction of... wait a second, actually. I maybe made a mistake here. No, I don't think I made a mistake. So if we're doing this one, my thumb is going in the direction here and my fingers are wrapping around this way, right? So in this direction. And if the magnetic field is going this direction, then right at this point P, the magnetic field is tangent to that point, so it's going in the direction here, okay? So now that we have this thing, we found out the total magnetic field at the center of the page. I can just expand this picture and show you guys what it looks like here. So we have two vectors pointing in similar directions like that. Since they're pointing in the same direction, I can actually add them up and they would give me the total length like that. Okay, so this is B and this whole thing is 2B. Remember that the magnetic field of a wire is actually this thing. So you can plug all these numbers in. You have the current and you have R. R is the distance from the wire to point P. If you have A and A, you can do A squared plus A squared, square root of that, Pythagorean's theorem, and you can find the distance R. And that equation we found here, remember? This equation, infinite wire. So now that we have that, let's go down here and take a look. I've already added these two vectors up, and since I have these two vectors like this, I want to add these guys up. This is where breaking things down into components comes into play. So I can break down these guys into components. I break down this guy into its x and y components, and this guy I break it down into the x and y components. You can see the y components actually go in the same direction. So since they go in the same direction, I can add this guy up and it would basically become double the length. But in the direction of the x, they're actually pointing in opposite directions, so these guys cancel. So to summarize, if you have four wires that are situated like this, a distance A and a distance A in a square location, in a square geometry, and you have the current coming out of the page for these guys and into the page for these guys, then exactly at the center, you would get a magnetic field that's pointing directly upwards. And you can find that using, again, some trigonometry and some of this. So that is an important thing to know about that, and a good problem to try out. Okay, so like I said before, we're going to take a small break. And what the break will be is just going over the physical constants again a bit slowly. If you want, take a little bit of a pause, get some water, go to the bathroom, get a snack, and we're going to dive into the rest of this equation sheet. We're almost done half of it. Yeah, okay, so let's take a look at these constants. Like I said, physical constants, this whole block here is very important because if you forget some units, you can go into here and use one of these equations to find out the units. So for example, well, actually, let's actually go through all the units. So we have E, charge of the electron. You have C over here, which is coulombs, and you have the magnitude 1.6 times 10 to the negative 19. You have Avogadro's number. Again, N is equal to 6.02 times 10 to the 23, and they actually give you particles per mole. So this many particles gives you 1 mole. That's how I think about it. We have C, the speed of light. The speed of light is 3 times 10 to the 8 meters per second. Coulomb's constant, 9 times 10 to the 9. This is Newton's meters squared, all of that divided by Coulomb squared. Cool. And you also get a different version of writing Coulomb's constant in terms of epsilon naught. 1 over 4 pi epsilon naught. If you plug all of that in using this guy here, you should get 9 times 10 to the 9. So epsilon naught, permittivity of free space, is this number here, times 10 to the negative 12. Coulomb squared over Newton meters squared. The same units as Coulomb's constant, except flipped, right? Because Coulomb's constant is 1 over epsilon naught, and epsilon naught is these units. So if you flip these units, you should get the units of Coulomb's constant. Mu naught, permeability of free space, 4 pi times 10 to the negative 7. Different units. Here you have Tesla, meters, and this is A for amps. Like I said, this guy, I don't really know it. Search up on Google what 1 Tesla in terms of capital G. Just search up 1 Tesla equals 10 to the 4 G. 10 to the 4 is 10,000, I think. Just search up 1 Tesla equals 10,000 G. What are the units? And you'll figure that out. Then we have 3 things for mass. Pretty simple. Mass of the proton, mass of the neutron, mass of the electron. Different masses, all of them in terms of SI units, kilograms. 1 electron volt equals this number of joules. So this is energy conversion. And like I said, let's say you're looking at some equation here. Let's say you're looking at, for example, infinite wire, and you're like, oh shit, I don't know what the units for the magnetic field are. Okay, no stress. You have the magnetic field here. It is straight up this equation. B equals mu naught I 2 pi A. Okay. You at least have mu naught. It is over here, right? So you have Tesla times meters over amps. That is the units of mu naught. Then you're multiplying this by I, and you know I has units of amps. Okay. So you can see amps and amps over here cancels. And you have this whole thing, all of this divided by 2 and pi. These guys don't have units, so you don't have to worry about that. And A is actually units of meters. So you have meters here, meters and meters cancels. And you can see all of this stuff gives you Tesla. So you know Tesla is the unit of the magnetic field in SI units. And you can do that with any equation here, right? Anything that you're looking for. If you're unsure about the units, I mean, once we get to this omega and all this weird stuff, you might be a little weirded out and confused by it, but just use the physical constants if you're unsure of what the equation is talking about. You can piece things together. Now that we're done with that, let's continue with our little break. To finish off the break, we're just going to go over these guys, and then we're going to be completely done this, and we'll finish off the entire video by going into these heavy hitter sections here. That way you kind of know every piece of info on this piece of paper. Keep looking at it over the next couple days, and you should be booling. And if you're confused by anything, like let's say we get to this and you're like, I don't know what this is, you could just go search this up and, educate yourself about it slowly. Don't go too ham on it. But over the next couple days before the final exam comes, try to look at it and ask yourself, where is the confusion? Okay, so very quickly here, we're going to go into kinetic energy. If you have the mass of a particle, let's say the particle is here, it has mass m, and it's going with a velocity v, you could take its velocity, square it, multiply that by m, and multiply all of that by 1 over 2, and you get k, which is energy. Okay, now remember when I said things about units? If you have energy here, you know that energy is in units of joules. You should remember that. Joules is energy. So you can have joules is equal to 1/2 has no units, but mass has units of kilograms, and velocity has units of meters per second. And since you squared velocity, you squared all of that. So take a look at this equation. Just because you know this equation and you know what each of the units in this equation means, you have a conversion between joules and SI units, kilogram meter squared per second squared. And since you have joules and you want to convert to electron volts, you can use this equation to convert to electron volts if you need it. This is kinetic energy, useful if you want to find the motion of an object or something. Like maybe they tell you a charged particle has 3 electron volts of energy. You can convert electron volts to joules, plug joules into here, divide by 1/2, divide by the mass, and you can find the velocity very simply. Same thing with angular. So this here is linear velocity, linear kinetic energy. And angular velocity is, let's say you have, you're sitting on one of those toys at the park that has like bars like this, and it's spinning around, and your friend is hanging over here, like chilling, but spinning very fast. He has an angular velocity of omega squared. And I over here is kind of like the mass. It's called the moment of inertia, I believe. Basically, you can consider it, it's not current. Capital I in this case is not the current. That's why they kind of put it in this box section away from all the electric stuff. the moment of inertia is literally just like rotational mass, you can think about it. So the same thing, you have these units here, plug that in and you get kinetic energy for a rotating object. Now, once we get to this guy, we have an object undergoing circular motion. So let's say you have a bucket of water, you put it in your arm and you spin your arm around. The bucket of water like this, you can remember like water just chills here, and as you spin it around, the water stays at the bottom of the bucket and it doesn't fall out. So this bucket is actually going around the circle with velocity v squared, and it has an acceleration here, which is v squared over r. So this acceleration is very useful when you do problems. So I'll actually show you guys a problem related to this this unit. Let's say you have a section over here which has a capacitor plates, right? Positive charge and negative charge, and it creates an electric field here, okay? And there's also a magnetic field pointing into the page in this section, okay? And then here you get into this new region where the electric field is turned off, but the magnetic field still persists. So what I'm drawing in red is the magnetic field. It is pointing into the page, kind of like a big magnet. This is B, and this is E over here. E is pointing down. So this thing here, this whole thing here is actually called the velocity selector. You may have seen this in some problems. And this whole thing over here with just the magnetic field is called the deflection chamber. So what happens here is a bunch of charges, a bunch of charge particles get shot into this velocity selector, and they're going in different directions. So one of them might come here, and it's going to feel a force due to the electric field. That force is the charge of the charge multiplied by the magnitude and direction of the electric field. It will also feel a magnetic force. Since we just learned about this, the magnetic force is proportional to it's proportional to Q, the charge, and proportional to this cross product. Okay, so it's going to feel these two forces. Let's say the charge is entering, and it is a positive charge, and it has a velocity going this way. If it's a positive charge and its velocity is going this way, the electric field will pull this charge this way. So the electric field will pull it in the direction of the electric field because it's a positive charge. If it's a negative charge, it would pull it in the opposite direction. Now, since this guy has a velocity v, it also will feel a magnetic force, right? So it feels the velocity. Well, it has a velocity going this way. So I can do the right-hand rule. Thumb in the direction of v, pointer finger in the direction of B, which is in this case into the page. So thumb, pointer finger, and the force will be directly upwards, right? This is the right-hand rule. So the positive charge will feel an electric force going downwards and a magnetic force going upwards. So based on the balance, if the magnetic force is stronger, it would go and maybe crash here. But if the electric force is stronger, it would go and maybe crash here. But if the forces are exactly equal, then the particle would go all the way through straight, and it would pass a little grating over here, where the grating just has one exit. So the particle will go all the way through, and it will make it here, and it will exit into the deflection chamber area. And the reason it's called a velocity selector is because, like I said, we need to have these forces be equal in order for the particle to not crash. If the electric field is a little stronger, or the magnetic field is a little stronger or weaker, then this particle will not go in a straight line. It would go maybe here, or maybe here, or maybe it'll crash here, and it'll just crash and it'll get stuck over here. It won't make it all the way out of the velocity selector. So since these guys are equal, let's straight up equate them. We'll do QE on one side equals QV cross B on the other side. Now, since the charge here is Q, it's the same on both sides and it's non-zero, we can cancel it. And since we have the cross product here, we can expand it using that dot product identity. V cross B is equal to VB sine theta. Now let's take a look at sine theta, the angle between B and V. If you look at V, it is going this direction, and B is going directly into the page, so the angle between these is 90 degrees. Sine of 90 degrees here gives you 1, so we can actually erase that whole thing, okay? Now I'm going to simplify this equation. On this side, I have the electric field. On this side, I have VB. And actually, I can find V in terms of E and B. I have electric field divided by magnetic field. So we've reached the first equation that's not included in the equation sheet. And this is the velocity that a particle feels in a velocity selector. You can see it depends on the electric field and the magnetic field. So you could think about these things as like hot and cold knobs on a sink. If you want the velocity to be a little different, like a faster velocity, like basically the particles exiting here have the velocity v is equal to E over B. If you want these particles to have a bigger velocity, you could just increase the electric field in this area, and the velocity selector will only allow fast charges to get out of there. Or similarly, you can decrease the magnetic field. So these things are like hot and cold, like knobs on a sink. You can increase E or decrease E, you can increase B or decrease B, and depending on these things, which you can control, like the engineer creating the velocity selector can choose, they can, by that way, select specific velocities. Okay, now that we know that a charge coming here, entering the velocity selector, will exit with a velocity V is equal to E over B. Once it exits here, it will enter with a velocity v going exactly this way. And since it has a velocity v going that way, and it enters a magnetic field, it will now feel only this force. Q is equal to V cross B. So we can do our right-hand rule, V and B in this direction into the page. It will feel a force going upwards like that. So you can imagine this particle enters this region. It has a velocity this way, but it feels a force going upwards due to the magnetic field. So slowly it gets pulled, and it'll actually do a circle, right? Let me actually draw that a bit cleaner. So what this charge will feel is actually a circular pathway like this, okay? And this will have a specific radius, r. Okay, so that is where that centripetal acceleration equation comes from, v squared over r. If you remember Newton's law, you can plug in F equals ma. In this case, what we have is mac, and this will give you mv squared over r. And on this side, what we have is Fb. The only force felt by this charge is the magnetic force. So basically, you have Fb is equal to mv squared over r. And this is an equation that can tell you what the radius of curvature for this particle in the deflection chamber is, right? If you want to find FB, you could just do QVB sine theta, right? That comes from QV cross B. And that comes from the force due to the magnetic field. Okay, very, very quick kind of problem with the deflection chamber introduction, and also that is where this equation here is used. AC is equal to V squared over R. Very quickly, the deflection chamber normally asks you what is the radius of curvature. If you have FB is equal to VB, sine theta we said was 1, and this gives you mv squared over r. This is Newton's law, ma, in this case a is the centripetal acceleration. Then you can manipulate all this and solve for r, and you get r is equal to mv squared, and then we have vb, and you can simplify this by canceling one of these guys. So mv over b. Yeah, that looks good. Yeah. Oh, we're missing q. My bad. Q over here. And the Q comes from this equation here. QVB sine theta. Sorry about that. Cool. So now that we have that velocity selector, we are still kind of in a little break. I'm kind of just going over these equations again. So we went over physical constants, kinetic energy, and Arc length, this is a very quick one. Actually, I'm going to do arc length and then we'll do kinematics at the end of the video, right? Arc length, like I said, here, if you have some little portion of a circle, and here you have the angle theta, and here you have the radius of the circle r, arc length, s, is literally the distance over here. This distance s, you can calculate it by doing r times theta. Very simple. You might not even need to use this, but very useful if you are dealing with something going in a circle. So okay, now we've done pretty much half of this video over here. Let's return to Faraday's law. Sounds good? We are now on to the Faraday's law, inductance, and LC circuits. Let's take a look at these equations, bird's eye overview, and then we'll dive into them one by one. So here we have one equation. We have an epsilon equals sign negative n. Capital N is normally for a number of things. And then we have a derivative, d dt of phi with a subscript b on it. So this is the derivative of the magnetic flux. So what this is telling you is time derivative of the magnetic flux times number of turns, number of whatever this is, times a negative sign gives you epsilon naught. So yeah, keep that in mind. We got another equation right over here. This looks like delta V, which is from the electric potential section. Delta V and epsilon normally are considered the same thing. They're like potential differences or voltages or yada yada. Then we got the electric field and length. This is actually an equation from the first half of the semester. I would say take a look at my previous video where we talk about the equation sheet, because this equation is included there. Then we got BLV, which is a little bit weird. I'm not too sure where this BLV is coming from. And then we have another equation which says basically the same thing. Epsilon naught is equal to negative BLV. So yeah, BLV here, epsilon naught, this, and then they give you this. Okay, interesting. And then there is no semicolon here, but you can consider this a separate equation because of this integral over here. So what this is telling you is this integral, if you remember from the previous video, is literally the definition of potential over here, if I'm not mistaken. So integral of E dot ds is equal to delta V. And this tells you that it's also equal to time derivative of the magnetic flux, as we saw in the first equation. And there's also this negative sign over here. Okay, cool. In the next line, we have three equations that look quite similar. We have epsilon, again, similar to this epsilon, except with a subscript L. So L is the inductor. And this over here, by the way, is Faraday's law. Faraday's law here, Faraday's law here. We're going to get into Faraday's law deeper, but just a bird's eye overview here. So you can see the voltage, or epsilon naught, the potential difference across an inductor L, is equal to the value of the inductor L, which normally is in units of Henry. So some number here. Remember how the capacitor was some number farads? The inductor is something similar to the capacitor, except units Henry instead of farads. Cool. Now we have di dt, so derivative of current with respect to time. Kind of weird. We've normally not seen that before. Normally we've seen current is equal to derivative of q with respect to time. But now we're getting this new variable, which is derivative of current with respect to time. Interesting. Next equation here is equation for L. L is equal to N times the magnetic flux over the current. Interesting. So N, flux, and current. And then we have another version of writing L, which is pretty much the first equation here manipulated. So you have L, and you have this di dt. You just move the di dt here, divided by this epsilon L, the voltage, and you also move this minus sign over here. So this equation and this equation fairly similar. This equation is pretty interesting. But yeah, those are the first couple of equations here. And then we have Another equation, which is, I guess, literally a copy of this one. So this equation and this equation, identical. No need to worry about that. Then we have I is equal to epsilon over R. This is very analogous to V equals IR for Ohm's law, except they replace voltage or the potential here with a epsilon. Then they multiply this whole thing by 1 minus e to the minus t over tau, where they tell you tau is equal to L over R. So again, very similar to the previous video I had for RC circuits. So for an RC circuit, if you remember, the current was something like I max, and then you multiply by this e to the minus t over tau, except in that case, tau was the resistance times the capacitance. And you also had another one where you had the 1 minus e to the minus t over tau. So I spoke about these in the previous video. They're charging and discharging functions. The inductor actually has very similar behavior, except slightly different, right? Instead of RC, it's L over R. You'll see this behavior following throughout, and you can compare it to the capacitor. But basically, this thing here tells you the current in a circuit with a voltage epsilon and resistance R and inductance L. So you can imagine the current through a circuit like this. So this is the resistor R and this is the inductor L. You can multiply these together in this format to get tau, and you can use epsilon naught, which is normally given to you, and R, which is normally given to you as well, to find the current as a function of time. Cool. Now we have this equation, like I said before, this 1 minus e and then this e. These two are charging and discharging functions. I think this one is the, let me see if I'm correct here. This is a decaying function. So it goes like this. So this is discharging. And 1 minus a decaying function is like this. So it starts at a maximum. This is 1. And then it subtracts a little. Wait a second. No. Hold up. I think this one is like this. Anyway, I looked over these two equations in my previous video and I plotted graphs of them near the end. So I would say check that out. But just for now, keep in mind that they are current inside a circuit with epsilon as the voltage source, R as the resistance, and L as the inductance. So here they actually write it a different way. You have I initial, which is the initial current, instead of epsilon naught over R. This epsilon over R is, again, Ohm's law, V equals IR. If you move the R on this side, you have epsilon over R is equal to I. Awesome. So that is this equation, and they also give you this one, and they have a semicolon here, U. If you remember, U is equal to potential energy, in this case, potential energy of a circuit with an inductor in it. So if you have an inductor, and there is current going through this inductor, it is current I, and the inductor is L. You take the current, square it, multiply it by the inductance, which, like I said before, is in units of Henry most of the time, and you can get the potential energy stored in this inductor. That equation is also included here, and you can see this is U, total potential energy, which is inside of a circuit with a capacitor and an inductor, so C and L. And you can see this is also from the first half of the year. Potential energy stored in a capacitor, you take the charge on the capacitor plates, square it, and divide it by 2 times the capacitance of the capacitor. Slightly similar, you have I squared here, analogous to Q squared. You have L, which is analogous to C, and you have a 1/2 term. So very similar behavior between the capacitor and the inductor here. Add these up together and you get the total potential energy stored in a circuit, and the circuit could look like this. Right, so let's say this is the circuit. If you have the charge Q stored on this and the current I going through that, and you have the inductance and the capacitance, you can find the total potential energy stored in that circuit. This equation I left out because I'm actually unsure what it's talking about. So this UB, I think, is again potential energy due to the magnetic field, and it looks like you have B squared over mu naught, and you also have U over V. So okay, let's just analyze this equation here together and take a look at maybe like analyze this and see what it's saying, because I'm actually unsure of what it's saying. So you have U, which I'm assuming is potential energy, and V, which is electric potential. Electric potential. And we have U, which is potential energy. I'm just kind of guessing here. I'm not 100% positive, but I'm positive that B here is the magnetic field, and I'm positive that this is mu naught. So like I said before, let's see what this is. So we have the units of B, which is Tesla squared, and we have 2, which has no units, and we have mu naught. So let's quickly check what the units for mu naught were. We got Tesla meters over amp. Cool. Let me plug that into my thing right here. Tesla meters over amp. Okay, and we see one of these guys cancel, and we get the total units, Tesla meters over amp. Again, wait, hold up. This has the same units as mu naught. Hold it down. What does that mean? And it's also telling us this. Okay, that's a little bit weird, but let's analyze this. So I said this is potential energy over electric potential. So I know potential energy has units of joules, it is an energy. And I know electric potential, well, let's peep this equation here. This equation here has electric potential in it right here, right? Delta V, potential difference in this case, E times L. Okay, and this equation also, I said before, was electric potential. Interesting. So let me just write that equation right here. So we have delta V is equal to electric field times L. This equation was very similar to the equation sheet in the first half of the semester, which was something like this with a negative sign there. This is the potential, or the electric potential, between 2 capacitor plates with an electric field E inside of them, separated by a distance D. So you multiply these guys together and you should actually get the potential difference between these points, delta V. And why I'm bringing it up here is because I know delta V potential has units of volts, right? That's the V. I know electric field has units of newtons per coulomb, and I know length has units of meters. So I guess joules over volts, I can write this, and this gives me Tesla meters per amp. I can also say this is Newton meters per coulomb. Actually looks quite similar. Newtons, Teslas, meters, coulombs, amps. And we have joules over volts. I'll be honest with you guys, I actually don't know what this equation is about. So big bird overview. I would say this is Faraday's law, which is what we're going to talk about right now. This and this little BLV, I don't know what it is. So take a look at that. That's the homework you guys can do. Just see if you can explain these couple equations. This over here is the use of Faraday's law again. So here we have this thing from the first half of the semester. This thing was defined as delta V. And we have delta V, which is also the epsilon here. It is the same thing. Delta V is a potential difference or a voltage. Epsilon naught is a voltage, like from a battery. And this is how you calculate potential difference in the first half of the semester. So this thing equals this. It's the same thing as Faraday's law here. Maybe they just give this to like show you more fundamentally how this equation came up. So yeah, I would say take a look at this specifically on your own. Also, take a look at this on your own. I'm not too sure what this is. I was doing a little unit analysis here to see if I can understand it, but I really can't. This here is potential energy. Then we have some circuit behavior over here and over here. So I'll maybe talk about the circuit behavior a little bit, But the main thing I want to talk about for this section is Faraday's Law. And here we also have the inductor, which is given to you in a couple different formats. So here and here, here, this is going to be quite important in the next section. But okay, big overview. Now let's talk about Faraday's Law, because I think that's the heavy hitter for this section. What does Faraday's Law say? So there is an induced EMF. This could be a potential difference, or it is a voltage, like kind of all synonyms here. Or sometimes they call it EMF. And the reason they call it EMF is because this is electromotive force. So I think the motive in that means like motional, like it is induced by motion, and you'll see why in just a second. So anyway, that's on the left-hand side of this equation. Then we have a negative sign. Sometimes we have this n over here, and then we have this time derivative. And then inside the time derivative, we have phi b, which remember is the integral of b dot dA. This was first introduced in Gauss's law. Except in Gauss's law, you actually take the integral over a Gaussian surface. And for the case of the magnetic field, if you take an integral over the Gaussian surface, this will always be 0. But if you don't integrate over a Gaussian surface, and you're just asking for, so a Gaussian surface was a closed surface like this, right? And this thing will give you 0, meaning there's no magnetic charge that can create magnetic field lines like this. It's always going to be some bar magnet thing, which has closed magnetic field lines. So the closed integral over a Gaussian surface is 0. But if you're just looking for the magnetic flux, which is, the magnetic flux is what this symbol denotes. If you're looking through the magnetic flux over some arbitrary area, then you can have magnetic field lines going into here, and this magnetic field could be B. And if you break down this guy into little area shapes, these area shapes have a specific direction as well. These are the dAs. Then how you find the total flux is you take the magnetic field here, dot product dA. Dot product is important because take a look at my Gauss law video. I was talking about the bubble blower and how if you blow a bubble this direction or this direction or this direction, it gives you a different kind of flux. And the flux is maximum at the same angle when cosine is 0 degrees. This gives you the maximum flux. So little bit of a rant there, but that is Faraday's law, and that is let's call it magnetic flux. This is number of loops. We'll get to that in a second. This is time derivative. And minus sign here, very important, negative, and induced voltage. So all of this is Faraday's law. Very, very dope. We're going to talk about this right now. And the cool thing about it is, okay, magnetic flux exists, right? Actually, let me draw this image first. So Faraday's law is basically saying, yo, we have magnetic flux, which could be created by a bar magnet like this, right? If there's a north side and a south side, let's just do north and south. This thing creates magnetic field lines, right? So there is a magnetic field coming out of this little bar magnet. If I take this bar magnet, let's just take this whole thing like this, and I move it, boom, in and out of this coil like this. As I move it in, if you take a look at the area that each of these loops has, the area is like this, right? This is the area of a circle. It's pi r squared, if this is r. And the magnetic field is going in here, and it's creating a magnetic flux, right? That's why you have this magnetic flux here. So if you have a magnetic flux and it's changing over time, like first of all, if the bar magnet here is just chilling in one spot, like it's chilling like this, then yes, there's a magnetic flux, but the flux is not changing. The time derivative is 0. So if the magnetic flux is just equal to like 3, whatever the units are, some random arbitrary units, then d dt, the derivative of flux, will give you 0. And then that means EMF is equal to 0. So if the flux is not changing, you don't get an induced EMF. Okay? If the flux is changing, however, like for example, I'm moving the magnet in and out, then you have an induced EMF. And what that induced EMF means is there's basically a potential difference here between these two things. And if there's a potential difference, there will also be a current. So if you attach this to like a light bulb, you would get a light bulb to glow by just moving this magnet in and out of these coils and by Faraday's law over here. So if that feels good with y'all, I'm going to take a slightly deeper dive into this by copying this onto the next page over here. So we got Faraday's law, boom, and we also have expanded this delta, or sorry, this phi b. It equals integral b dot product dA. And actually, let me replace this dot product with b dA cosine theta. Okay, so the main thing you have to notice is if this derivative d dt phi b is not equal to 0, then you get an EMF, induced EMF, right? And the way it can change is 3 different ways. One is you have the magnetic field is a function of time. So if the magnetic field is like sine of t and some numbers, then it's changing, like I'm moving it back and forth, I'm growing it and shrinking the strength of the magnetic field. So when I take a derivative, this will not equal 0 because derivative of sine t is cosine t. Okay. Another way is if you change the area. So here I'll actually write area as a function of time equals, some area. So the problem I've seen here is you have a circuit which is with a resistor like that. And there is a metal conducting rail that you can take and you can move like back and forth along this circuit. So this circuit will have a length x and a height y. And if I change the length of this bar, then I am changing the area because the area is y times x. So I'm increasing and decreasing x, which is increasing and decreasing the area. And let's say here I have the magnetic field all like this, like everywhere in the circuit there is a magnetic field. So the magnetic field is creating a flux on this entire circuit over here. And since I'm changing the area, I'm changing the flux. And this would actually create a voltage from here to here. And that means current would start flowing in the circuit if I'm changing the area due to Faraday's law. So the area can also be a function of time. Now finally, the last thing that can change is theta, which is the angle between the two of the things. So the example I've seen here is you have a magnet set up like this, where you have a north and south side, and the magnetic field lines here are going like that. So in here, you can actually place a little square wire like that. And if you attach this thing to like a drill, like let's say here you attach to a bar and you staple this bar to this little metal coil wire and you start applying a torque on this, like you start turning it, then this little loop over here will start rotating. And since it's rotating, the angle between B, so this is B, and A, so A is the vector that is in the center of this thing, and it is the length of the area of this whole thing, and it's pointing perpendicularly outwards. So in this picture exactly, you would have the vector A and the magnetic field B in this direction, and as the thing spins around, you would have A spinning around like this, right? It's spinning around, and for each of those, the angle theta is increasing, and then it reaches a maximum, and the angle changes. So basically, you can have magnetic flux, which is the integral of B dA cosine theta, or B dot product dA. The magnetic field can always increase or decrease, and if it's doing that, it is a function of time. The area of the circuit in question can be changing in time, like this, if the area here is shrinking and growing, and there's a magnetic field permeating the circuit, then magnetic flux is changing with respect to time. So you will have a non-zero derivative, which will create voltage or current. If you have Ohm's law, if you have a voltage across a resistor, then you will get current flowing through that resistor. And this is a voltage due to Faraday's law. And finally, if you have theta, which is kind of like this little engine here, if you're changing the angle between the loop and this thing, you are also changing the flux. So that will create a voltage onto these things, and you can actually connect these also to a load, which is just like a regular battery or a light bulb, and this would power that. This has a resistance R. Cool. So now that you know those couple examples and how Faraday's law uses this, I mean, the main thing, the main principle is magnetic flux has to be changing with respect to time. Also, if this is happening through multiple loops, so it's happening through one loop, right? This is one singular area, A. Then you have another loop, A, and another loop behind it. You have this equation applied n times, like 1, 2, 3, 4, 7 times. So you place this with 7, and you increase the induced field. So if you get 1 volt produced by just one coil, do 10 coils, so plug the 10 into here and you'll get 10 volts. So you could just increase that. In this case, you have this circuit. If you have the same circuit all applied like below it a million times, you would increase it as well. Here, if you have this thing, but it's instead a bit thicker, and you wound like a bunch of wires around it, and each of these wires can provide current, then you also increase it by this number n over here. All right. Cool. So now that you know this, let's just take a look at this equation sheet. That is Faraday's law over here, and that relates to this thing over here as well. Faraday's law is normally just d dt phi b, and it creates a voltage, which is this thing. Like voltage is defined as this thing in the first equation sheet. Okay, so that is the main Faraday's law. And one other thing I wanted to say about Faraday's law is you have a couple examples here of problems that they can ask you. So let's say we have a magnetic field like this going into the page, and it starts over here. And we have a little loop like this with resistance R. So let's say I take this loop and I start moving it with a velocity v going this way. Here it enters the magnetic field, passes through. Here it's fully into the magnetic field. It's going into the magnetic field. And here it exits the magnetic field area and it's fully out. So let's say we had a couple examples. We had one. Let me duplicate this. This is 2. Duplicate this again. This is 3. Duplicate. Duplicate again. So we have a couple examples here. Let's label these as 1, 2, 3, 4, and 5. So this is just different times of this thing, since it has a velocity v, different snapshots in time. So 1 is when it's completely outside of the magnetic field moving towards it. 2 is when it slightly enters, so the right side is a little bit inside the magnetic field. 3 is when it's fully inside. 4 is when it's exiting and the magnetic field is just applied to the left side, and 5 is the same as 1 except it's outside. So the question is, what is the direction of the current that is applied, that is created onto, that this little loop feels at each of the stages? So in location 1, I would say I is equal to 0 because it's not entering the magnetic field, it's just moving. The whole loop is moving. There's no other information that would tell us that there would be a current going. So that's what I would say. So this is for 1. For number 2, we have the loop slightly entering the magnetic field, which means the flux is changing, which means a voltage should be created. So due to Faraday's law, we have negative d dt phi b, and in this case, phi b, can I even say what phi b is? Let me see. So what I was saying is, in this scenario here, the loop is slightly entering, and there's small flux being created here, and then here, and then here. So the flux is slowly increasing. So since this function is slowly increasing, the derivative is going to be a non-zero number, which means a potential difference will be created. Because of that potential difference, you can expect a current to appear in this loop. Now, if we just want to find the direction of this loop, or the direction of the current in the loop, we can use another equation that we learned earlier that can help us. But if you want to find this induced EMF, you need to find the equation for the flux, which is a little complicated in this scenario. I mean, we have velocity, but the flux will slowly increase. It will reach a maximum value here, and then it'll decrease, right? So it's a little bit complicated, but okay. Imagine that these little charges on this part of the wire, they're going this direction with a velocity v, and they feel a force due to the magnetic field. The magnetic field is into the page. So you can do your right-hand rule, v cross b, and the middle finger is pointing completely upwards, right? So the force due to the magnetic field on this side of the loop, the force will be upwards. So you can imagine if all of this charge wants to kind of go in this direction, and this charge is doing nothing because it's not feeling the magnetic force yet, then all of this charge will push and start creating a current going this way. So the current for that one, I would say, is I is counterclockwise. Cool. Now, what's happening in the middle is, and again, like that current is actually created by this epsilon, and this epsilon creates a current through Ohm's law, V equals IR. And another thing we're going to talk about is this minus sign, because you may have also learned about Lenz's law. So we'll get to that in a second. But okay, once this thing is in the middle, the force due to the magnetic field on each part of this loop is upwards, because the whole loop is moving with a velocity this way, and the magnetic field is always facing this way. So thumb in this direction, pointer finger in this direction, the force due to the right-hand rule will always point upwards. And since each part of the loop feels this force upwards, then there will be, again, no current. So I will point that here. And I guess we can also answer part number 5. So each of those cases, there will be no current. 1, 3, and 5. Part number 4 is a little different because this section feels nothing, but this section is still moving this way with this velocity. So this guy would feel a force going upwards. Again, FB. And that means the current will now be going this way because it has nowhere else to go. So for part number 4, I would say the current is going I is clockwise. You guys see what I'm trying to do there? Okay, now let's see if we can kind of explain from actually Faraday's law what is happening here. So let's say we have a loop of wire like this, and we have a north-south magnet over here. north and south. So the magnetic field lines leave the north and enter the south, if I'm not mistaken. I would say confirm that just to be sure. So here they're going this way, and they're going like that, this way, this way. So in this scenario, they're going here. If I take this entire magnet and move it in and into the magnet, so I am let's actually make this magnet a bit smaller because I'm gonna have to use it a couple times. Duplicate it and put it right here for the time being. So we have this set up here, and this magnet has a velocity going into this thing here. Okay, so that means the magnetic flux will be kind of this way, right? And since it's going closer, the magnetic flux is increasing, right? So you can imagine the magnetic field lines due to this north pole are getting stronger and they're facing this way. Because they're getting stronger, the magnetic flux is changing, and let's pull up Faraday's law here. It will induce an EMF, and that EMF will have a negative sign compared to the change in the flux. So this flux is changing, right? This flux is getting stronger when we're moving this bar magnet closer to this thing. So its derivative is it's a big number. This induced EMF will counteract this change in flux. That's Lenz's law. Moving magnetic field will create equal and opposite voltage or current. So how you can think about this is this guy is moving downwards. It's increasing the magnetic flux. So the potential is going to create a magnetic field which opposes this one, opposes due to this magnetic sign, opposes due to this negative sign here. So if the magnetic field lines here are growing, meaning it's getting stronger because the magnetic field is coming closer, then this loop will create a current which has a magnetic field pointing the opposite direction. So this is induced B. So the coil will create its own magnetic field to resist the change created by this bar magnet. And because of this magnetic field is only created because of the current in the wire. So there's many ways you can think about this. One is the magnetic field in this location is increasing because the flux, this thing is coming closer, the magnetic field lines here are stronger, and the flux is changing. If the flux is changing, you get a voltage onto this wire, and you get a current going in it. Or you can think about it as the magnetic field here is increasing. From Lenz's law, we know that a changing magnetic field like this in a current, in a little wire like this, will counteract the magnetic field. And how this is happening is straight up due to Faraday's law. So like we said, there is a voltage created on this, which creates a current going this way or this way. And the wire is like, hey, there's an increase in magnetic field happening here. So I'm going to create my own magnetic field in order to stop this, in order to like go back to the normal like status quo magnetic field. So now since we have the magnetic field of the wire, this is the induced magnetic field due to this changing flux. We can find the current which would be needed to create this magnetic field. So you can use your right hand rule again, thumb in the direction of the let me see how I can draw this. So right hand, thumb in the direction of this, and your fingers wrap around this way. So your fingers are wrapping around this way, which means the current, which I will draw in yellow over here, is going around this way. You can also do your right hand rule another way, so point your thumb in the direction of the current, and you can see that in the middle, you create this magnetic field here. Cool, so that's the scenario where you have the coil right below you, and you are moving the magnet towards the coil. Let's say we're now moving the magnet away from the coil over here. So the magnetic field here is still pointing, it is still pointing downwards, right? This is the magnetic field due to this bar magnet. It's the same magnetic field like this, except now we're moving the bar magnet away from this loop. Since we're moving the bar magnet away, the flux over here due to the magnetic field is decreasing, okay? And since it's decreasing, the derivative is still non-zero, and because there's a changing flux, you get an induced EMF again. But think about this. The flux now is getting weaker, so the loop itself is the loop wants to maintain the status quo. So it's like, yo, I am sensing the magnetic field or the magnetic flux going through my area is getting weaker. Since it's getting weaker, I'm going to create more magnetic field going in the same direction as the magnetic field I feel in order to counteract this weakening of the magnetic field. You see what I'm saying? So the induced magnetic field due to this scenario is going to be in the downward direction, right? Very different from this scenario. In this scenario, we had this magnetic field increasing because I'm bringing the magnet closer. So the loop is like, yo, relax. I don't want to feel all this magnetic field. I'm going to create my own opposing magnetic field in order to counteract all of this big flux that I'm feeling downwards. So this induced magnetic field is created by this current, which itself is created due to Faraday's law because there is a voltage induced onto this thing. But you can think about it in multiple different ways. Okay, in this scenario, we have the loop and the magnet is moving away from the loop, which means it still is pointing this direction, right? The north side is the emitter, so the flux is going to be the north side of the magnetic field pushing in like this, and then it would loop around and join into the south side over here, right? But it's still facing downwards. So the direction of the magnetic field is downwards, but its strength is decreasing, right? Because we're moving this magnet away. So this loop is like, yo, I'm feeling a magnetic field going downwards, but it's getting weaker. And I don't want it to get weaker. I want it to stay the same as what it was. So I'm going to create my own magnetic field. This is the magnetic field that the loop itself creates in order to counteract this change. So again, this magnetic field is created by the loop because there is a current running in the loop. Why is the current running in the loop? Because due to Faraday's law, we have a change in the flux. The change in flux is literally happening because the magnet is moving up and down. And this change in magnetic flux creates a voltage on my loop. And if the loop has a resistance like R, it creates a current. And we learned a current creates a magnetic field. So this is what Lenz's law is talking about when it's mentioned as like the law that resists changes. This is what it's talking about. Now let's look at the other two scenarios where we have the magnet. I'm going to copy this magnet again. And this time, we're going to see what happens if it is on the bottom side of the loop. So in this scenario, it is moving up. In this scenario, it is moving down. And the loop is over here. So, okay. In this case, it's moving up, but the south side is now closer. So the magnetic field is actually going down, right? It's coming around like this from the north side, up and then down into the south side. And now the south side is closer to us. Same thing here. So it's emitting from here and going into here. And since this magnet is getting closer, the magnetic flux is still like this. It's pointing in this downward direction. But the magnetic flux is also increasing because the magnet is getting closer. So if we draw what the loop responds to, the loop will be here. And it's going to be like, yo, I'm feeling a magnetic field coming downwards like this. And it's also getting stronger. There's more of these lines coming in. I don't like this change, so I'm going to counteract this change by creating my own magnetic field going upwards in order to stop this growing of the flux. You see what I'm saying? So this is the induced B. And because of this induced B, you can use the right-hand rule. Thumb in the direction of the magnetic field, and the fingers wrap around in the direction of the current. So in this case, they're going to wrap around like this. And the current is going like that. That is I. So again, right-hand rule with the current creates a magnetic field like that, which counteracts the change in the magnetic field from the magnet. Change in the magnetic flux, to be very precise. So yeah, same thing there, same thing there. And let's take a look at this last example. So again, magnetic flux is downwards, right? Because we have, that is the south side. It is getting emitted here, and it is entering that way. Okay, but now the flux is getting weaker because the magnet is being pulled away. So how the loop will respond to this is it's going to look at it and be like, okay, I feel a magnetic field going downwards, but this magnetic field is getting weaker. So in order to counteract this weakening of the magnetic field, I will create my own induced B, which is going in the same direction as this weakening magnetic field, because, you know, I don't like this weakening. The wire is like, let's relax, bro. I want to stay back to where we were. I want to be like, I don't like change. It wants to resist change. So now that we have this induced B, we can do the right-hand rule again. Thumb in the direction of the magnetic field. In this case, thumb is pointing directly down, and this gives us a current which goes like this. All right. And again, if you want to find the magnitude, you have to find the actual change in the flux, right? Faraday's law. Change in flux could be a function. Take a derivative of that function with respect to time, slap on a negative sign, and boom, you get EMF. Okay, guys, it's getting kind of late, so I think I'm going to cap it off here, and I will do the circuitry section another video because I want to release this for y'all. So that finalizes this. I guess I could talk about more of these things. Like I said, I don't know what this equation is, and I don't know what this is. So I would say take a look at that on your own time. This I also didn't talk about. This is omega, which is, it's an angular frequency. It's related to L and C. And when we get to AC circuits, I think that will make a bit more sense, this omega. And we also didn't cover the kinematics, but we covered this magnetic force, this whole thing is magnetic force here. We covered some physical constant stuff. We covered this thing here, and we just covered this with a little thing on Faraday's law. So I'm going to finish off with AC circuits. I'll try to post that very soon, but I'm trying to go to sleep right now. And we got the kinematic section. Cool. Make sure you look at this. Make sure you Google search whatever you think is confusing to you. Make sure you check a couple problems. Literally search up the equation, the name of the equation, and problems. Take a look at as many problems as you can. Practice the final exam. And yeah, let me know if you guys have any questions. Thank you very much for listening. Thank you for paying attention. Good luck. Yeah, stay warm out there. Stay hydrated. And, you know, meditate. Call your family. Call your friends. Talk to some, you know, relax. Take deep breaths. You're going to be chilling. Don't worry about it. I know it's kind of crazy looking at all these equations, but, you know, stay zen. You're going to be bulling. All right, I'll talk to you guys later. Bye.